All right, so we got the divers leaping off of a platform into a pool, blah, blah, blah. They give us a horizontal distance from the edge and a vertical distance from the water to the shoulders of the diver as x of t and y of t in meters, and starts at 11.4 meters above the water, and there's our equations. So the first thing we want to do is we want to find the maximum vertical distance from the surface of the water to the diver's shoulder. So to find a vertical maximum, we should just be setting our dy dt value right here equal to 0 to figure out at what t value that happens. So we will say dy dt equals 0 when t is about, what did it come out to be, 0.367. No, that's not right. Yeah, okay, 0.36735. Yeah. Cool. So that's what you got for that, hopefully. Yes. 3.6 over 9.8. Yep. Okay. Cool. And we want to actually find the maximum vertical distance. So in order to figure that out, we need to integrate the dy dt value from 0 to this t value. So we'll say the integral from 0 to 0.36735 of 3.6 minus 9.8 t dt. And then we'll have to add to that the initial amount, which was started off 11.4 above. And that came out to be 12.061 meters. Everybody okay there with part A? Any issues with part A? Okay. Okay, then so part B, we want to find A, which they're calling the time that the diver's shoulders enter the water. And so that would mean that we would need to be at a position of 0 in the y direction. So our position at any given time is given by our initial position plus the integral from 0 to some value. We're going to talk about a t value of a. So 0 to a of 3.6 minus our 9.8 t dt. Our same dy dt. And we want to know for this, when is this thing equal to 0? And so you'll need to actually integrate this. So you'll get, so we'll do it over here. We'll get 11.4 plus 3.6 t minus 4.9 t squared from 0 to a is equal to 0. And obviously this, when we plug in 0, is going to become 0. So really we're just plugging in a and then solving for a. And that came out to be, a was about 1.936 seconds. Does that make sense for part B? Yeah, so from the beginning, Shayla, or just the ending part, or? Yeah, all of part B, okay. So we want the position of the diver's shoulders to be 0, because that's when we'd be hitting the water, because we started 11.4 feet above the water, right? And so the position of 0, and so we wrote an equation that represents the position of the diver's shoulders which is the initial position plus the integral from the initial position, or the initial time of 0 to some value a, which is when we want to hit the water, of the y component of our position, dy dt. And we set that equal to 0 because we want to know when the diver's shoulders hit the water, which would be a height of 0. So this is a representation of height, and we've just set it equal to 0. We just integrated 3.6 minus 9.8t to get 3.6t minus 4.9t squared, and then evaluate it from 0 to a. The 0 is just 0. So we end up with 11.4 plus 3.6a minus 4.9a squared. And we just want to know when that equals 0. So you would just graph that on your graphing calculator and get that value of 1.936. Does that make sense or no? Cool. All right. Part C, find the total distance traveled by the diver's shoulders from the time she leaves from the platform until when her shoulders enter the water. So this time we've got to deal with both dx dt and dy dt. This should just be an integral from 0 to a. And now, since this is like, this is particle motion, essentially, she's moving in a plane, just it happens to be a vertical plane, but moving in that plane, that xy plane, should just be the square root of dx dt squared plus dy dt squared, which they give you both of those. And we found a in part B, and so you just integrate, and you should end up getting 12.946 meters. Oh, I should probably be telling you guys what all the points are worth here. So for part C, you had 1 point for the integral and 1 point for the answer. Part B was also 2 points, 1 point for setting up an equation and 1 point for the answer. And part A was 3 points, 1 for setting dy dt equal to 0, 1 for having this integral here, and 1 for the answer. Okay, so everybody good with part C? Okay. All right, so then part D is saying find the angle theta between the path of the diver and the water at the instant the diver's shoulders enter the water. So we are we're trying to figure out the angle between the diver's shoulders and the water. And so that should be just a slope of the line that is tangent to the path of the shoulders, right? So that's not what, we need to find that slope. So we can find that slope, dy dx, by getting dy dt over our dx dt. And we know that the time period that we're interested in would be when t is equal to a. And so that gives us negative 19.21913. And so if we go back to our picture and we think about this, the shoulders entering and the water here make some, well, I didn't mean to do that. I screwed myself up. They make some sort of looks terrible. We're making some sort of angle with the water here, right? And so whatever that angle is, we should be able to figure out the path of it, because we talked about the direction of motion way back when. The direction of motion was given by the inverse tangent, right? So it took the inverse tangent of the slope of that path. And so the inverse tangent of negative 19.21913 tells us that, let's see, what did that come out to be? 1.518 radians. So about pi over 2, pretty darn close to pi over 2, which makes sense because if we're thinking about this, I mean, diver should be entering pretty much straight vertically at almost a 90-degree angle there to the water. Good or no? Yeah, we're always talking about a positive angle. Yeah, so yeah, you're right. So if you put in inverse tangent of negative 19.21913 or whatever, that's just because the diver is going down at like a very steep negative slope. But they asked for an angle between, they said between theta and pi over 2, right? Yeah, between 0, I don't know, said between theta and pi over 2, between 0 and pi over 2. So we're looking for a 90 degree, something, something between 0 and 90 degrees. And so, yes, it's got to be the positive version of it. So you can just take the inverse tangent of the positive version of negative 19.21913 or whatever it is. Yeah, that's one of our particle motion things, Nick, is that the inverse tangent, right, of the inverse tangent of your velocity, and this is what this is that's what dy dt and dx dt, that's right, that's your velocity in the y and the x direction. So the inverse tangent of that should give you the direction of motion. Any other questions there on that? All right, anybody have any other questions on any of the particle motion problems that I assigned yesterday, or just any of them in general? What is my laptop doing here? Somebody said something. I think I got all messed up. Part D of the third one. Okay, what was the third one? So this one? No, that's not one. This one? Okay, part D. Somebody else has said something here. No, not that one. This one? Does that look right, Delphine? Is it this one? Okay. Sorry, I didn't see that you'd responded. Okay. Anybody want any other parts of that one before we move on to just going straight to part D? Okay. All right. So part D is just asking if we have a time t greater than or equal to 0 at which the object is on the y-axis. So we've got an object moving in the xy plane. So we want to know if it's on the y-axis. That should tell us that let's see, we got tangent of e to the negative t and secant of e to the negative t and a position of 2, negative 3. So what we want to try and figure out then is basically, does the x component ever become 0, or is our x component always positive? So effectively, is our value for x ever going to cross through the x-axis? So we can first off know that since we said originally, it said at t equals 1, it was at 2, -3. So we need to figure out what it was at t equals 0 to figure out if it was ever potentially to the left before it was at t equals 1. So to figure out where its position was at t equals 0, we'll need to take its x position at t equals 1, which is 2. And then let's see here. So we'll add to that the integral from 1 to 0 of our dx dt value, which is tangent of e to the negative t dt, to figure out its position at t equals 0. So if you want to, you could rewrite that as 2 minus the integral from 0 to 1 of tangent of e to the negative t dt, if you feel better about it that way. But let's see, I don't know. Somebody tell me what that is on the calculator. I don't have the scoring guide for this one. So anybody got that value? 1.224. Okay, that seems reasonable. 1.224. So that's also positive. So we know that it starts at a position that's to the right of the y-axis. That starts at an x value of 1.224. And let's see here. What else here? E to the negative t. So if we think about e to the negative t, e to the negative t, if we're going to, let's see here. A tangent of e to the negative t. So e to the 0 is just 1. And we know the tangent of 1 is positive, so it should be moving to the right at that point. And if we were to try to figure out if this has any critical values, we'd have secant squared of e to the negative t to see if that had any critical values. And secant squared, or secant itself, is never going to equal 0. So we know that there are never any places where this equals 0. The only places where this equals 0 are places where it might be discontinuous. And so places where this is undefined would be places when 1 over e to the t is undefined, which would mean that e to the t would have to equal 0, but e to the t does not ever equal 0. So this thing never equals 0, and this thing is never undefined, which tells you that tangent of e to the negative t is either always positive or always negative. And since we've already shown that it was, we knew that it was already positive at t equals 0, we know that dx dt is always greater than 0. And if we started to the right and the direction of motion is always moving to the right, we're never going to be on the y-axis. Does that make sense or no? That was a good one. Quite a little thinking there. Cool. Any other questions on any of the problems from yesterday? And I believe these were like 2006, 2007-ish, maybe 2009 questions, something like that. So if you're looking for the scoring guides for them, that's which ones they are. Most of you probably already went and checked your work on them, I'm guessing, yesterday. But all right. So here's what I would like to do if there are no other questions. Oh, wait. Yes, Nick, that's right. Dx dt is always positive, which means the object always moves to the right. Exactly. And since it started to the right of the y-axis and it's always moving to the right, it will always be to the right of the y-axis. All right, let's see here. So I would like you guys, just as a little bit more practice on the improper integral stuff, I came across another one that I guess I'd missed when I was making your differential equations packet of things last night, and came across this one that I guess I missed when I was looking for ones with improper integrals. So we got f of x is 1 over x, g of x is 4x over 1 plus x squared for x greater than 0, and we're looking for assorted areas and maxima, minima on intervals and all that fun stuff. So this one I don't think should be too difficult, but I'd like to give you guys about 15 minutes there to work through, and then we'll talk about it. Sound good? All right, you have 15 minutes. Ready to go. So part A just wants us to find an absolute max and an absolute min on the interval from 0 to infinity, non-inclusive, if they exist, and to justify our answers. So that should be pretty straightforward. We just got to find g prime of x to start with. So finding g prime of x means we got to use the quotient rule. So we got 1 plus 4x squared times 4 minus 4x times 8x all over 1 plus 4x squared. And you simplify that all down probably here to get, let's see, that's 1 plus 16x squared minus, or sorry, 4 plus 16x squared minus 32x squared. So that's 4 minus 16x squared. Over 1 plus 4x squared. And we know that nothing's going to make our denominator equal 0, so it's never going to be undefined because 1's positive and 4x squared is positive, and positive plus positive is a positive, and any positive squared is definitely not 0. So clearly the denominator is never 0. Anything that would make that 0 anyway would make the original function undefined, so we don't need to worry about that. So we'll just set the numerator equal to 0. 4 minus 16x squared equals 0, and that gives you x equals positive or negative 1/2. Obviously, we're going to ignore the negative 1/2 because we're only talking about the interval 0 to infinity. So we just got positive 1/2. And we will make a sign chart with positive 1/2, cutting ourselves off at 0, going towards infinity. So we plug in something like a fourth to this. 4th squared is a 16th. 16 times a 16th is 1, so our numerator is positive. And the denominator, like we said, is always positive, so we're increasing. And if we plug in something more than a half, like 1, we get negative over a positive, so we're decreasing. And since these are the only critical values at a half, and we're increasing up to a half and decreasing after, this must be the local max as well as the absolute max of that function on the interval 0 to infinity. So we have a max, and did it ask us to find the max? Yeah, find the actual value of the max. So g of 1/2 should be 2 over 1 plus 1. Looks like it should be 1. So we have a max of 1 at x equals 1/2. And then we will say that there is no absolute min because there's only the one critical value. is a max, as well as there are no endpoints to check. If there are endpoints to check, then we might have an absolute min, but since there are no endpoints to check, we don't have one for sure. Part A should have been pretty straightforward, basic, like, I mean, you should have been able to do that without even hardly thinking, I hope. Everyone good with part A? And somehow they gave 5 points for that. Not for that, for the whole thing. So 2 points for getting the correct derivative, 1 point for finding the critical value of a half, 1 point for your answers with your justification. Oh, 1 point for your answers and 1 point for the justification. So 2 points for all this down here. All right, so then the second part then asks us to do some actual BC improper integral stuff. We want to find the area of the unbounded region in the first quadrant to the right of x equals 1, below f, and above g. And so we need to do an integral from 1 to infinity of the upper function, which is f, minus the lower function, which is g. So it should be the integral from 1 to infinity of 1 over x minus 4x over 1 plus 4x squared, I think. Yeah. And so they will dock you points on these if you don't rewrite it as a limit. So the limit is, it doesn't really matter what variable you use. We'll say a to infinity of the integral from 1 to a of 1 over x minus 4x over 1 plus 4x squared dx. And that should give us a limit as a approaches infinity of natural log absolute value of x. And then this one should just be a simple u sub, right? If u is 1 plus 4x squared, then du is 8x dx. So I would need to put in a 2 with an extra 1/2 out in the front of that. So this will end up becoming minus 1/2 the natural log of the absolute value of 1 plus 4x squared. And obviously that one, the absolute value is insignificant on. We can eliminate it because it's redundant, but we can do that in the next step. And so now we can go ahead and try to simplify this down. So if we can, we always want to simplify the logarithmic expression. So we'll call this a limit as a approaches infinity of the natural log of, and we'll say the absolute value, but we only need the absolute value on this because we know that all of our values we're plugging in are positive, 1 to infinity. So we'll just say of x over root 1 plus 4x squared, bringing in the 1/2 power to that 1 plus 4x squared. And then we'll just plug in our values. So a goes towards infinity, natural log of a over root 1 plus 4a squared, and then minus natural log of 1 over root 1 plus 4. Everybody good with that so far? As a goes towards infinity. Somebody said something there. Could I use inverse tangent for the integral of g? No, because it would have to be like a constant up here. If this was a constant up here, then you could use inverse tangent for it. Right? Like if you wanted to make that 1 plus u squared with u equal to 2x, you would just need to have a 2 dx up here to do that with, but you have 4x. So yeah, if that was just a constant, you could. Okay, so we'll finish this off here. So the first part of it, a over the root 1 plus 4a squared, the base powers of those are the same, right? That's like having, we square root that. It's basically like having just a 2a down here. So this part becomes natural log of 1/2, and then this is minus a natural log of 1 over root 5, which isn't the greatest looking answer. So we could probably rewrite this as natural log 1 minus natural log 2 minus natural log of 1 minus natural log of root 5. If we wanted to rewrite those, all the natural log of 1s go away. We got a negative ln 2 plus ln root 5. So we got ln root 5 minus ln 2, which would be natural log of root 5 over 2, which would be a good enough answer if we wanted to leave it like that. I think the scoring guideline has it as 1/2 the natural log of 5/4, which is also fine. So just rewrite this as square root of 5 over the square root of 4, pull the 1/2 out, and it's 1/2 natural log of 5/4 is what they wrote, but our answer is good too. And that was worth 4 points for all of that. 1 for the right integral setup, 2 for having both the antiderivatives correct, and 1 for a final answer. Good or no? Feel all right about improper integrals still? Any questions there? Natural log of 1/2 minus natural log 1 over root 5 should be fine, yeah. I mean, there's nothing that says that this is better or worse than this, other than this just looks nicer. But they don't specify to simplify it down to something like with no radicals or something, so you should be fine if you left it. All right, so we will have one question like these partial fraction, decomposition, or improper integral ones. We'll have one question that is a particle motion question on the quiz on Monday. You can expect probably particle motion one to be a calculator and the other one to be a non-calculator, most likely. So expect that. And then we will now start talking about differential equation for your response questions. So for those of you that were in AB last year, we did a fair amount of work with the differential equations, and some of them are going to be pretty similar, but a lot of them now incorporate, they get a little bit more difficult, a little bit more parts to them, and sometimes also include Euler's method as a part of it. So there's one up here above this one about a potato that we did this potato one last year. This was also used on the BC test. So I recommend doing this one, but it's only got AB material, so I want to move into one that's got some BC stuff. This is more like what I would expect you to see. You could potentially see these fun like potato type problems, and we'll practice a couple of those eventually, but I want to start with one of these ones that has a little bit more fun, difficult stuff. This packet, if you are asking in the chat, is posted in the assignments category of the Google Drive, along with all of the other ones. Should be about 20 of them, it looks like. All right, so we're going to do this one first, and then I'm going to say, if you have time over the weekend, it'd be great if you could do let's say the potato problem, number 1 and number 3. So yeah, 3 is a good one. It doesn't have any specific BC stuff, but it's kind of a pain, especially the last part of it. So we'll do 2 right now in class, but I'd like you to do 1 and 3 before class on Monday. Cool. So I will give you 15 minutes. We'll work through this one right now. We won't go over this one till Monday after the quiz. First thing on Monday will be the quiz, but 15 minutes right now. Ready, go.